Have you ever noticed how the once shiny surface of a metal turns dull and rusty after being exposed to the elements? That's corrosion in action, and it's a process we see in everything from old vehicles to iron bridges. Let's take a closer look at how this happens and what causes metals to deteriorate over time. So, corrosion is a chemical process where metals react with their environment, usually oxygen, water, or air, leading to their gradual breakdown. One of the most common forms is the rusting of iron, and it's a perfect example of how redox reactions unfold in real life. Just like when you leave an apple out and it turns brown, metals, too, are prone to oxidation when exposed to oxygen.
Corrosion is not just about metal turning into rust, it's about a redox reaction, a process involving both oxidation and reduction. Let's break this down with iron rusting. At the anode, iron reacts with water and oxygen, losing electrons. Now, at the cathode, oxygen from the air gains those electrons in a reduction reaction, leading to the formation of water. Together, these reactions create iron oxides or rust, and it's this process that weakens the metal over time. Now, let's dive a little deeper. Corrosion behaves like an electrochemical process. Imagine the metal surface divided into tiny regions, with some areas acting as anodes and others as cathodes. The electrons that are lost at the anode travel through the metal, causing corrosion to spread. At the cathode, oxygen is reduced, further accelerating the rusting process. This is very similar to how a battery works, with a flow of electrons between the anode and cathode. The result? The iron, which started as a solid metal, gets eaten away and transformed into something else entirely. So, how do we stop this from happening? One of the simplest ways is to coat metals, shielding them from the elements. You've probably heard of galvanization. It's when a metal like iron is coated with a layer of zinc. Zinc acts as a sacrificial anode, which means it corrodes first, protecting the iron beneath it. Imagine a knight in shining armor stepping in front of an attack to protect what's behind. That's exactly what the zinc does. We can also use paints or other coatings to create a barrier between the metal and oxygen, and in some cases, metals are alloyed with others that don't rust, like stainless steel. Corrosion isn't just a classroom concept. It affects our daily lives. Consider the ship hulls in the ocean or the pipes buried under the ground. These are all exposed to harsh conditions, making them prone to rust and corrosion. That's why engineers work hard to design structures that can withstand corrosion for as long as possible. For instance, marine vessels are made of special corrosion-resistant alloys to prevent damage from salty sea air. And it's not just metals. Think about the corrosion of the wires in your household appliances too. But why do some metals corrode faster than others? Well, it comes down to their electrochemical potential. The more reactive a metal is, the more likely it is to lose electrons and corrode. That's why metals like zinc and magnesium corrode easily. But metals like gold or platinum, which have lower reactivity, are far more resistant. Think of the periodic table as a chart of reactivity. The higher a metal's position, the more reactive it is. So, the next time you see rust, just remember, it's not just dirt. It's a reaction happening at a molecular level, powered by the electrochemical potential of the metal. Seawater is a special case. With all its salts and ions, it's a powerful accelerator of corrosion. Iron rusts much faster in seawater than in fresh water, and that's why metal structures near the coast are more vulnerable. The chloride ions from salt water interact with the iron, making it much more prone to corrosion. This is why engineers use materials resistant to corrosion, like stainless steel, when building offshore platforms or ships. It's also why bridges and piers in coastal areas need frequent maintenance. To sum it up, corrosion is more than just rusting. It's a redox reaction that involves the oxidation of metal and reduction of oxygen. We learned about the electrochemical nature of corrosion, how metals lose electrons and become weaker over time. But don't worry, corrosion is not unbeatable. We can prevent it through techniques like galvanization, coatings, and even using sacrificial anodes. Remember, corrosion doesn't just happen in labs or textbooks. It impacts our daily lives, from rusting cars to the protection of infrastructure. So, next time you see a rusty nail, you'll know it's not just dirt. It's a chemical battle in action. Hope you enjoyed learning how corrosion works, and I'll see you next time for more chemistry magic.